So now let's describe how global linear models, GLMs, can be applied to dependency parsing. So throughout this section, I'll take X to be a sentence. So X is going to be a sequence of words, X1, X2, up to X sub n. And really, to define a global linear model, we need to give two definitions. So firstly, we have to define gen, that takes a sentence as input and returns a set of candidate dependency structures as its output. And secondly, we have to define f, which is a function that takes a sentence together with a dependency structure and returns a feature vector representation. So gen is going to be very simple. It is simply defined as the set of all dependency structures for the sentence X. So for example, for John saw Mary, gen of the sentence will return all possible dependency structures over these three words. Critically, the size of gen is exponential in n, where n is the length of the sentence being parsed. So we're again in a situation where gen is going to be a very large set of possible structures, at least for appreciable length sentences of say 10 or 20 or 30 words. This is going to be an extremely large set. So f, of course, is going to be a function that takes as input a sentence in conjunction with a particular dependency structure and returns a feature vector. So it might return some vector like this, which is the representation used by the learning algorithm, used by, for example, the perceptron algorithm when setting the parameters of the model. And we'll see that there is a way of defining f that gets us around this problem of the exponential size of gen, because we can again use dynamic programming for search for the most likely tree under this model. So let me now talk about how we can define f. So the key idea is going to be, again, to define f as a sum of local feature vectors. So remember, in the last segment on the perceptron algorithm and global linear models for tagging, we saw a very similar thing where f was defined as a sum of local feature vectors g. In the dependency parsing case, we're going to have one local feature vector for each dependency in the structure y. So y is a structure, and this is going to be mapped to a set of dependencies where, again, each dependency has a head and a modifier. The head is an index of a word, where 0 is the root word, and the modifier is also an index of the word in the sentence. The local feature vectors can look at any information in the sentence and can look at the identities of this head and the modifier word. So let me illustrate this with an example. So here we have a sentence X with a dependency structure. So the sentence X is John saw a movie. So we have X1 equals John, X2 is equal to saw, X3 is equal to A, X4 is equal to movie. And the dependency structure Y is basically equal to a set of dependencies where we have 0, 2, 2, 1, 2, 4, and 4, 3. So it'd be useful to number these words 0, 1, 2, 3, 4. So for example, the dependency 2, 4 corresponds to this directed arc between saw and movie. Now we're going to have some feature vector mapping that takes x in conjunction with I and return some feature vector. And through the definition on the previous slide, this was defined as sum over all dependencies in y of g of x hm. So for this particular example, this is going to be g of x 0, 2 plus g of x 2, 1 plus g of x 2, 4 plus g of x 4, 3. So again, we're playing this trick where we define a global feature vector as a sum of local feature vectors, where now we have a local feature vector for each of the directed arcs in this dependency parse. So we might, for example, have feature vectors like the following. So maybe our 4 feature vectors look like the following. And in this case, the sum would be 1, 2, 3 in the first position, because I have 3 1s and 1 0. Just 1 in the second position, because I have 1 1 and 0s elsewhere. In the third position, I would have 1, because again, I have a single 1 in the third position. And in the final position, I also have 1. So that's going to be the final global feature vector. It's a sum of these local feature vectors. Again, what we're seeing here is something which is very common in these kind of models, which is that these local feature vectors have 1s or 0s. These are going to be features, we'll talk about this more in a second. These are going to be features which ask various questions about these different dependencies. And then the global feature vector is going to be a count. For example, there were 3 dependencies within this structure such that this first question was true, i.e. the first question had a value of 1. So let me give you an example of how we might define these feature vectors. So maybe the first feature, so this is the first component. So we're going to have g x hm is going to be a vector composed of functions g1, xhm, g2, xhm, right the way up to g sub d of xhm, where d is the dimensionality of the feature vector, is the number of features. So each of these different functions g1, g2 up to gd will look at an xhm triple and return some value. So one such function might be the following. So this is 1 if x sub h is equal to soar and x sub m is equal to movie. Okay, so in particular we would have g1 of John saw a movie, and if we have 2, 1 as the dependency, so that's this particular dependency here, this is going to be 1 in this case. Okay, so this particular function, this particular feature, looks at the 2 words that stand in some dependency relationship between xh and xm and returns 1 if they're a particular word, 0 otherwise. We would typically define a feature like this for every possible pair of words in the vocabulary. Okay, so again, as we've seen often with these log linear models, we might have a very, very large number of possible features, 1 for each pair of words. These features are very useful because certain pairs of words are very likely to stand in a dependency relationship. Other pairs of words are much less likely to stand in a dependency relationship. Let me give you some other examples of features. It's very common actually to not just include the words in the input x, but also to include part of speech tags, because those can provide useful information. And so now if we have g2 of xhm, here's another feature. Now think of x as including both the words and also the part of speech tags in the input. So you could say something like 1 if the part of speech tag for h is equal to VBD, and the part of speech tag for M is equal to NN, 0 otherwise. So these kind of features would be introduced for every possible pairs of part of speech tags in the underlying part of speech tag set. And these kind of features are very useful because certain part of speech tags are much more likely to be seen in dependency relationships than other ones. Another type of feature which we might use could look at the distance between the two words. Okay, so we could say this is 1 if the distance between H and M, so the difference, this is the absolute value of the difference, is equal to 10 and 0 otherwise. So this feature returns the value 1 if the two words involved in the dependency are very far from each other. And these kind of features can be useful because there's certainly a statistical tendency in language for these dependencies to be between close-by words. That's actually an empirical observation which holds across many languages. You do see occasional dependencies which are very long, but many of them are these short dependencies where we just have an adjacent word, or we have a dependency involving words within a 2 or 3 word window. Now what you'll hopefully see from these examples is we have considerable freedom in defining these features, which look at the sentence, the index of the head word, and the index of the modifier word. We can incorporate all kinds of information about the words XH and XM, maybe the part of speech tags for those words, maybe the distance between those two words, maybe surrounding information. So we could look at the part of speech tags or words to the left or right of the two words which stand in the dependency relationship.